In this video we're going to look at how we would calculate Kp. So a question like this, where you've got a certain number of particles of a reactant being compressed to form an equilibrium, which gives us a product in equilibrium with the reactant. You might also get some kind of amount of the reactant left over, or you could equally have a certain amount of product in the question. And the aim here is to calculate the Kp from the data. So first of all, Kp is equal to the partial pressure of the products divided by the partial pressure of the reactants raised to the power of the number that's on the front of them in the balanced equation, the stoichiometric number. So, in my example, we are going to use N2O4 as our product, so that's going on the top. It's a gas, and we're going to have the partial pressure of NO2 gas on the bottom, and in our equilibrium there is a 2 in front of the NO2 in the balanced equation, so that term is going to be raised to the power of 2 or squared. So as you can see, it looks very similar to a Kc expression, it's just instead of concentration we are using partial pressure. We're going to need that equation, but we're going to need some information from the question first. We're going to draw ourselves a table. We want to know the initial moles of substance which are in the container. We're going to need to know the change in moles as the reaction happens, and we're going to need to know the number of moles at equilibrium. So our reactant is going to be NO2, and that's going to be in a 2:1 ratio with N2O4. And from the question we can see that we only have 1 mole of this in the container to start with, and we know that at the end, see that's there, 1 mole NO2, that's there. We know that we're not going to get anything else in there. This implies that it's empty, so we know that this initial number of moles is going to be 0. We also know that from the question we have 0.2 moles of NO2 left over at the end. So again, that's this column here. We've got NO2 at the end of the when it's formed equilibrium. We're going to have this number here. It's going to be 0.2. The question now is, how much of this do we form at equilibrium? And we work that out by working out the change between these two. This one is 1, this one is 0.2. This is exactly the same as you do it with the Kc expression so far. We are going to have a change of 0.8. And that's going to be our change. Now, this is a reactant, so I'm losing 0.8 there. And this is a 2:1 ratio, so for every 2 of these particles we are going to make 1 of these, which means that a 2:1 ratio means that this change is also going to happen 2:1. Every 2 particles of this used up, 1 of these will be made. So 0.8 divided by 2 gives us 0.4. Because this is the reactant, it was negative, this is the product, we're going to have plus. Which means 0 to start with, 0.4 added to it gives us 0.4 as our number of moles of equilibrium from the N2O4. We now need to know the total number of moles, and if we add these two values together, we can see that that is 0.2 added to 0.4, that gives us 0.6 of a mole of particles in totality. So if we are now I'm going to use X as a symbol for mole fraction. Mole fraction is how much of the total gas is made up by this one here, goes there, and how much of the gas is made up of this one here, goes there, as a decimal fraction. So we've got 0.2 out of the total of 0.6. That's 0.2 divided by 0.6 is a third, isn't it? So we're going to write that down as 0.333. And in this column here, we've got 0.4 divided by total of 0.6. When you add these two together, that's going to be 0.667. Now I'm rounding all of these to three significant figures. When we do that, we should see that the mole fraction should, in theory, add up to 1. So if we add those together, we do in fact get 1. So as the total is 1. So we've got our mole fraction. We know that this fraction is made up of that gas, this fraction is made up of that gas, and we now need to know the partial pressure of the gas. So the partial pressure means that if we have a third of the gas being this gas, then or this chemical, then that means a third of the total pressure is going to be made up of this particular gas's contribution. So we're going to take that number, we're going to times it by the total pressure. The total pressure is in the question up here, 2 atmospheres, and the unit is going to be important when we come to give the units. So 2 atmospheres of pressure, a third of it is made up of NO2, and so 0.333 multiplied by 2 gives us 0.66. Now, because this was exactly a third, I've left it in my calculator and I've times that by 2. That comes out as 667. Okay, but when I'm writing the table out, I'm going to round to 3 significant figures whenever I write something down. So in the other column, we've got 0.667 is the mole fraction. We're going to multiply that by 2 as well, and we get 1.33. Now, my mole fractions added up to 1, and my pressure should add up to 2, and you can see here that I'm going to add 0.667 and 1.33. That actually comes together to make 1.997, and that's just because I've rounded it in the table here. If I use the calculator values, it does come out of 2, but if I add these two together and round it to 3 significant figures, it still comes out as 2.00. And that's a little check you can do to make sure that you've done the mole fraction and the partial pressure right. The mole fraction should add up to 1 every time, and the partial pressure should, of all of the things added together, should add up to the total pressure at the end. Now we're going to use our Kp expression to calculate our value for Kp. We've got the partial pressure of N2O4 is this one. So that's going to be 1.33. We're going to divide that by the partial pressure of this one raised to the power of 2. And when we put that into our calculator, it comes out as 2.9996. That's a 9, honestly. 6. And so that rounds up to 3.00, to 3 significant figures. Do pay attention to the question. Sometimes the question will ask for a certain number of significant figures or decimal places. I always go to 3 significant figures by default. unless I'm instructed otherwise in an exam. And now we've got that, we just need to know the units. Now we work out the units in the same way as we worked out the units of Kc. We saw in the question that the pressure is in atmospheres. So that means that to calculate the atmospheres, we can say the units are going to be equal to, this is in atmospheres, ATM, divided by, and this is in atmospheres, ATM squared, which means we can cancel that out with the square, which leaves us with 1 over atmospheres, and so our answer is 3 ATM to the power of minus 1. Note that you can have lots of different units of pressure. Atmospheres is what was in my question here. If it was kilopascals, there's actually no difference in how you work it out. It's just you write kilopascals in there instead. There's no need to ever convert a unit of atmospheres to kilopascals when you're dealing with this sort of question.